All right, I'll get started. So just a couple things. Again, the quiz is this Friday. Probably don't have to tell these people here because you guys were here last Friday probably, or Wednesday. But the lecture from that Wednesday has been a little bit slow to get online due to some technical issues, which I think that I figured out, but I didn't have enough time this morning to upload it to YouTube. So it looked like I was able to upload it to YouTube, but it takes about an hour to physically upload, and I couldn't leave my computer at home because I needed to bring it in. And meanwhile, anyways, there's issues. Hopefully I'll have it up tonight. If you it'll probably be up at some point tonight, but more likely tomorrow morning, because I'll have to go into my website and actually put it there so you can actually find it. Otherwise, you'll have to go and dig through my section, I guess, in YouTube, which has been growing. In terms of topics moving forward, I think, with a lot of the stuff that we're discussing now, it's sort of exposing you guys to a lot of particularly biological molecules, and a lot of it's, it's a lot different than what we've seen in the past. So a lot of it is not really much practice-based, but a lot of reading and stuff like that. So it doesn't have quite the problem-solving aspect to it. What I think I'm going to do, especially after sort of looking at today's chapter, is I'm going to spend some time today. I'm going to get through all of lipids today. So I'm just going to get through all of lipids today. I'm going to talk about some of the things that I think are kind of interesting about them. I think some of the things that put at least this class of molecules into perspective for you guys. But again, it's not going to be too much in terms of reactions or anything else like that. And then I'm going to move into sort of peptides and amino acids. And so instead of having 2 classes on peptides and amino acids, what we're going to do is we're going to have 3 classes on them. The first class, I'm actually going to go over pretty much what's in the book. So I'm just going to explain to you guys what peptides are, amino acids are, enzymes, and so forth. And then what I'm going to do is the next class, so whatever, that would be November 26th. And I'm putting this information on the website. I'm in the process of updating it on the website, so you can actually go and find this stuff on the website. On the 26th, what we're going to do is we're going to talk about peptide and enzyme synthesis from the perspective of organic chemists. And so the book alludes a little bit to this idea of solid phase peptide synthesis. It's basically how, as you can imagine, if you're doing lots and lots of reactions, again, I'll discuss it then, but it's just sort of a standard way that people have gone about making peptides and amino acids, and there's a couple different ways that you can go about it. So you can sort of read a little bit of it in the book, but I've sort of just given a website link that's actually from a company that sells peptide synthesis material, and so it sort of explains the sort of process. And I was looking through websites that I thought did it in a sort of a nice and straightforward way, and they seem to do a nice job of it, and we'll go into a little bit more depth on that. But what I'm going to spend quite a bit of time is there's some really cool chemistry that's been developed in this area called chemical ligation. Again, it'll make sense once we get to there, but the idea is that when you do chemical synthesis of peptides, enzymes are huge macromolecules, right? There are lots and lots of these, and we'll discuss them in more depth in next class, but there's a lot of these amino acids within larger enzymes, and so when people are putting these together, as you can imagine, you're losing material each time. And so there's strategies that people have done that allow you to do some pretty fancy chemistry on subunits. It's actually really selective chemistry, and there's some interesting mechanisms within there that I think you guys will be able to appreciate at this point. But it's this concept called native chemical ligation. There's really 2 reasons I'm going to talk about it. It's not in your book, but we're going to be responsible for it. And so there is some material on the website sort of that you can read through. But it's really cool chemistry. I think that it's chemistry that you guys can definitely follow, that's in line with what we've seen. I think it'll put into perspective how synthetic chemistry-based solutions can sort of come into play in biochemistry, which is the course that many of you will take next, and so at least you'll sort of get that flavor. The other thing is that one of the sort of pioneers in this technology of chemical ligation is actually going to be our Friedman lecturer this spring. His name is Tom Muir. And Tom Muir, native chemical ligation was first developed, and again, we'll talk about this by guy Steve Kent out in California. And Tom Muir was a postdoc in his group and actually developed this technology as a postdoc and has continued working on it and made huge strides along the way. So I think by exposing you guys to this stuff, that'll be nice, because then you guys, if you haven't been to Friedman lectures, you should go. They're phenomenal. And so the Friedman lecture in the fall, which will be, I think, it'll be posted at some point, but it'll be him. And so by showing you guys some of the chemistry, hopefully the Friedman lecture, if you go and see it, will actually make a little bit more sense, which I think would be a nice thing for you guys. But that'll just be on the 26th. The following day, I'm actually going to be giving a talk at Queens College. And I asked Professor Geronimo Navarra to fill in for me. And he does a lot of work with peptides and stuff like that. So I thought it was a good opportunity for him to just come in and talk about his research to a certain extent with you guys. So try to put into perspective the type of work that we've done within that context. So he'll come and he'll give a talk. A lot of you guys had him for first semester organics. So he'll be coming and he'll be talking a little bit about his research. And I told him what we would be talking about. So he's going to try to relate what he's talking about then. So I thought that would be a nice addition as well. So both those things I think will at least give you guys a perspective of actual research that's going on, that's current, both here, right upstairs, as well as the sort of work that's ultimately going to be the Friedman lecture. And then we'll move forward and we'll talk about some of this other stuff. But that's just to give you a heads up. Again, the material is going to be on my website. If I find anything else that's I think is really good, I'll post it there. If I have time, I'll put together like a little worksheet. But again, you guys know what I like. I like mechanisms. So if you guys are looking at the reactions, know the mechanisms, because that'll help you appreciate them more. And there is some pretty neat mechanisms within some of these chemistries. So this stuff's not in your book, but definitely pay attention to the mechanisms of those transformations. And again, that's what we'll be discussing the next few classes. Okay, but today our focus is going to be on lipids. One more announcement, and I guess I'll make this announcement at the end as well, just in case anybody has to leave early and is planning on coming to my office hours today. We have a faculty candidate today, and I'm meeting with him at 11:30. So my plan is, a lot of you guys come and only stick around for like a half hour. So I'll start my office hours at 11, but then I'm going to throw you guys out at 11:30. But then you can come back at 12. Okay, so once I'm done meeting with him, you can come back from 12 to whenever. Well, that's not true. I have to go to a seminar at 2. But, if you guys, up until about 2, you guys can hang around. So again, if you show up and there's some guy that you've never seen in my office at 11:45, that's the reason why. So if you want to show up at 12, show up at 12. If you just have a few questions, come by at 11, but I'll throw you out at 11:30 when he shows up. Okay? All right. So with that, we'll talk to you a little bit today about lipids. So again, lipids are another very important class of organic molecules. So given the sort of information that you guys have learned to date, we'll discuss them a little bit today. We'll put them into perspective in terms of areas that you may have seen them, and sort of given what you've learned the past few semesters in organic chemistry, you may be able to have a better appreciation specifically for what these are. So in general, when we're talking about lipids, one of the first things that we're often associating with lipids are what we'll call fatty, quote-unquote, fatty acids. Okay, and what we're generally talking about is carboxylic acids where your R groups are really, really long, right? Like N equals, 6, 7, 8, 9, 10, like huge long compounds. N equals greater than, I'm just going to make up a number here, but the point is they're long. Let's say greater than 5, right? Maybe even 10 plus. So the point is that these are molecules that have very, very, what we often refer to as greasy side chains. So these are just carbon-hydrogen bonds. They can be unsaturated, so you can imagine having alkenes in them and so forth, and we'll discuss some that are like that. But this is mostly what we're talking about, is we're talking about molecules that are generally fatty acid derived. So what you have is carboxylic acid, and then you have really long side chains. And so the sort of name fatty acids, sort of in a way, comes from the sort of terminology in terms of when we think about fat and the components within fat being largely composed of these types of things. And that's why you also hear like grease. People talk about, as a med chemist, sometimes we'll talk about in our design adding grease to molecules. And basically what that means is adding hydrophobic components to something. And so again, it comes with that name of what we think about as grease. and then associating that with the molecule name. And so you'll hear names like fatty acids, you'll hear about greasy residues sometimes, you'll hear people talking about them like this. And again, when they're talking about greasy, they're just talking about hydrophobic, long hydrophobic groups. So again, just sort of carbon-hydrogen-based molecules. And there's some certainly important properties that we have with these. And again, within where you guys often hear about molecules, right, we talk about a couple different classes of lipids. So sometimes you talk about sort of saturated fats. Again, we've heard these terms saturated and unsaturated. Do you guys remember what this term means? Sometimes it's, I think, hard to keep in track. Yeah. Yeah, so it means saturated with hydrogens, right? So when we talk about something that's saturated, we mean that effectively everything in that molecule is there's no double bonds or rings or anything else like that. Okay, so you've got a molecule like this one here, which is basically got 12 carbons total, and this one's lauric acid, so this would be an example of that. But what you also have is you'll have molecules that are that have double bonds in them as well, and so we'll see these on occasion. And these, as you might imagine, are called unsaturated fats. Okay, and so an example of an unsaturated fat would be something like oleic acid. Which is again big and long and greasy, but it has this sort of cis double bond in it. Now, this sort of term, unsaturated fats, right? What's kind of interesting, I remember when I sort of learned this, I was like, oh, that's what they're talking about. So we know that alkenes, right, are highly are sort of the cis alkenes are actually more reactive, right? And so it turns out that in your body, this is generally your sort of natural make sure I word this right. Sort of the natural unsaturated fats are very commonly and generally, they have cis double bonds in them. Okay? Now, some of you may have sort of gone and bought some chicken nuggets from the grocery store and it says no trans fats, right? And what that's basically the result of is, especially things like butter products and margarine and things like that, people will do and take fats, right, and they'll oftentimes do sort of processing to them, which involves chemical modifications. And so a lot of times what will happen is if you have some group of molecules, you can effectively attenuate the consistency of it, or you can attenuate certain properties of it by simply, again, you can imagine a mixture of different fats, and if you have a certain percentage that have alkenes in them and a certain percentage that don't, there's going to be perhaps different consistencies within them. And you can imagine that by doing things like hydrogenation chemistry, right, you might be able to now generate more unsaturated fats than saturated fats. Right, now the issue is cis double bonds your body can metabolize fairly readily. It can do oxidation, and that's the thing, is that once your body can take unsaturated fats and take them to more polarized molecules, that becomes easier for your body to then get rid of them. So your body can clear them out. And so we talk about metabolic pathways and metabolism and stuff like that. Oftentimes, this is sort of what we're talking about, is metabolism is often thought of as sort of oxidative processes whereby you're degrading molecules. A lot of times that's dealing with sort of molecules like an alkene. So your body doesn't really have a great way of getting rid of just greasy molecules. But the way that it generally will do it when it can is to effectively take the cis double bonds and oxidize them and do other things. Now, as I sort of said earlier, this sort of processing of things such as like butter to try to make different consistencies, it'll also involve hydrogenation. Sometimes what can happen in hydrogenation through the process is that a lot of your cis double bonds, instead of being hydrogenated, will actually just be isomerized. And so through the process of that, what ends up happening is you end up generating a bunch of trans double bonds. And once you have those trans double bonds in there, now your body can't process them as easily, so they just stay in your body and your body can't get rid of them. And so that's why when you read something that says no trans fats in it, that's generally what it's referring to, is that they've been careful to make sure that whatever processing might be done or the ingredients that go into them is going to be devoid of trans fats that would likely have resulted through unwanted byproducts from, say, for example, hydrogenated conditions and stuff like that, okay? So again, you'll see sort of that, when you read unsaturated fats, generally what they're talking about is these. When they're talking about trans, that's Y. But then to the same extent, saturated fats and fully saturated fats, as you can imagine, can also be difficult to get rid of. So certainly there are natural fats, but again, the ability to metabolize them and get rid of them and clear them out becomes more difficult. So that's why sometimes you'll hear of good fats and bad fats. Sometimes that can be associated with how easy it is for your body to actually get rid of them once they've served their purpose. So that's kind of interesting, I think. The other thing about fats that we see a lot is that, and it's sort of interesting about them, right, is that they have sort of two groups of them, right? If you imagine taking this molecule, right, the pKa of a carboxylic acid is what? 5, right? And so pH of water is 7, right? So if you're sitting in water, acetic acid with just a little bit of base, right, can effectively, when you're at a pH of about 7, generally the carboxylic acid is going to be mostly deprotonated, right? So what happens is if you have a molecule, especially in the deprotonated form, where now you have a big grease chain and you've got some sort of ionic head groups, say with sodium, right? If sodium's that happens to be the ion in there or something like that, what you end up having is molecules that will effectively have one part of the group be very polar, right? Or we can say hydrophilic. And this part will be hydrophobic. Right? And this is one of the big reasons why fatty acids are often used in things like soaps and detergents and stuff like that. Because what happens is you basically generate molecules that have extreme groups to them. And when you put a molecule like this, right, and if it's going to assemble, right, in the way that you would perhaps expect it to assemble, you would assemble with the hydrophilic components of the molecules being together, and you would imagine the hydrophobic components of the molecules being together. And so if we imagine a molecule where we sort of drew this something like that, where this is the hydrophobic and this is the hydrophilic, and you guys may have seen this type of stuff in the past, what will happen is you can imagine, as this begins to sort of form, what you end up getting is micelles, right? Because you start to align these groups, you start to stack them this way, and when you're in, say, an aqueous environment, what happens is you end up getting, effectively, right, these sort of spherical, sort of what we call micelles, right? These are sort of spheres. Where on the outside, right, you have sort of the hydrophobic components. On the inside, you have the hydrophilic components. And the reason why you would form a micelle like this in an aqueous solution, right, is that you have all of your water out here. Right? And so these are the groups that are going to want to bind with the water, right? So you'll solubilize, you'll have all the water on the outside, right? So then you'll have all of the greasy molecules on the inside. Right? And so these types of things are actually used quite a bit. Obviously, the general way that we think of these compounds, again, is things like soaps, right? Because if you have a bunch of, say, grease on your hands from cooking that steak, right, and you are trying to wash it off, what's going to happen is all the grease will end up in the middle, right? And effectively what will happen is the micelle will trap these little pockets of grease, right? Because if you just take water and grease, what's going to happen? Nothing, right? Because the water will just slide right off, right? But in the presence of soap, what will happen is you will effectively form cages around the sort of grease pockets, and then meanwhile create these little globules of these spheres that are effectively soluble in water, but in the middle of them they have grease, right? And so this is the property that makes many soaps what they are. It also actually has found a lot of value in drug delivery vehicles as well. So the book doesn't, I don't think, discusses this, but I think this is kind of neat and worth mentioning as well. That a lot of times, we talked about your body. Many of you guys are sort of interested in health and stuff like that, so I thought this was sort of interesting. A lot of times when we take drugs, right, there's a certain lifetime that they have, right, and that's going to be different from drug to drug, and really what that comes down to is how fast your body is able to metabolize it or get rid of it, process it in some way. And so one of the things that people can do, right, and so that's a problem that doctors will have, and many of you guys that become doctors will find that, right, your patients aren't taking their medications regularly, and you're getting pissed off, right? Like my wife gets pissed at me when I don't give my dog the Claritin that it needs because it has allergy issues, right? So especially if you're treating something that's worse, right? People aren't very good at getting on regimens. We're just, as humans, I feel like we're more prone to disorder. So you can imagine if you only had to take a drug once a week, or if you only had to take a drug once a month, right? That would be a lot better, right? Instead of having to take it every day. And so one of the things that people are actually exploring now is ways to take molecules that perhaps wouldn't degrade, but that would, for example, release compounds into solution. And micelles are sort of a common way that people will do this. So what they'll do is they'll take, say, some type of polymer like this. So they'll take polymeric units, and it'll be pure. And then what they'll do is they'll take some drug. Again, drugs are generally depending upon the drug, but oftentimes they're more organic soluble than they are water soluble, right? And so what will sometimes happen is that you'll mix these together, they'll do some interesting chemistry. I don't really understand the sort of nature behind it, but they'll somehow get it to assemble in a way where what you'll have is, again, as you can imagine, the sort of micelles, right, around the drugs. Right? And then usually what's oftentimes within these sort of micelles are things like things that would degrade slowly in the body or something like that. So they would have some type of group on there that would degrade slowly. So now instead of the drug being instantly released into your body, what it does is it will slowly release it into your body. So you can imagine taking the drug once and then that would slowly, it would almost be like a little catheter or something. Not actually, catheter would be the reverse. Whatever basically some type of, injection that would just be constantly going into you, and that's kind of what this would be. Yeah?
What would degrade? Just slowly let it out?
Yeah, so sometimes, so we talk about metabolisms and stuff like that, metabolic degradation. Sometimes there'll be like groups on here that would have some type of functional group on them that would then get oxidized and degrade or something like that. Again, I don't know the specific details. People will do different things. What this also opens up the possibility to do is that sometimes people will also coordinate these to things like antibodies that will selectively now go bind to, say, for example, tumors, right? And then it will just stick around in the tumor and slowly release the drug as well. So sort of micelles, sort of micelle formation is sort of, we've seen it in soap, but again, people are now actually sort of using it. Biochemical engineers and so forth are trying to sort of use this in terms of encapsulation methods for delivery of drugs and things like that. So it's cool, but again, it's just based upon this sort of principle of having one part of the molecule be hydrophobic and the other part be hydrophilic to sort of form these capsules. Okay? All right. Okay, here's something else that's interesting. So another class that's really important among the sort of saturated fats, the book discusses a couple of classes of molecules, and one that I'm actually fairly familiar with from my days in graduate school involve sort of arachidonic acid cascade process. So arachidonic acid, So arachidonic acid is a very sort of important therapeutic fatty acid. And the general structure of it is something like this. Okay, so this is arachidonic acid. Again, you can sort of see it's got all these sort of cis double bonds in it. And what arachidonic acid is it's the sort of precursor to a variety of molecules called sort of eicosanoids. So if you ever heard the term eicosanoid, eicosanoids are molecules that are formed from arachidonic acid. So completely possible I misspelled that. That's the sort of general name of it. Again, I'm not sure if the book uses that name. But the eicosanoids that you guys might have heard of in particular are prostaglandins, which are really a group of molecules, but several within that group are involved in sort of triggering inflammatory effects, right? And one of the key steps in the pathway to a variety of prostaglandins is something called cyclooxygenase. Okay, you guys may have heard of this without knowing it. It's called COX. So one or two. So you guys have heard of COX inhibitors, maybe? That might have been something you guys have heard of in the past. So COX inhibitors are molecules that effectively inhibit the cyclooxygenase pathway. A great example of this would be ibuprofen, for example, right? So ibuprofen has inflammatory effects because it effectively inhibits this pathway, effectively disrupting the ability to form a whole variety of different prostaglandins. And so the molecule that's formed through the cyclooxygenase pathway a key intermediate okay, so when you go through these sort of cyclooxygenase pathways, what you get to is really oxidized species, such as the one that I've shown you here. And then it turns out that there's further modifications that can be made to molecules like this that will lead to effectively these prostaglandins. Okay, so this is an intermediate towards prostaglandins. This is an example of one prostaglandin. And again, this is an example of a prostaglandin, one example of prostaglandins. That triggers inflammation. So this molecule that I've sort of shown on the right-hand side there, that, again, when your body generates that, that will effectively signal to the rest of the body to effectively begin to upregulate different immune things like, all right, generate more white blood cells or, whatever the inflammation response is going to be, right? And so, again, it's these cyclooxygenase inhibitors that sort of do this. Now, one of the problems with disrupting a specific step within a sort of biochemical pathway, right, is that things are sort of super complicated, right? So if you identify a target that might be interesting in terms of having potential therapeutic value, med chemists will oftentimes spend a lot of time trying to disrupt that one pathway. And if that one pathway, say, involves some parasitic disease or something like that, then as long as you can selectively try to target that one parasitic organism or, say, a bacteria, right? If it's only found in that one bacteria, that's fine. And you want to kill that bacteria, that's fine. You target that and there's not going to be a problem. But a lot of times, things that are more associated with sort of innate human sort of health, like specific pathways that we have physically, is that oftentimes these pathways can be important, right? And so if we inhibit one pathway along that road, other things can sort of begin to happen, right? And so one of the issues is that when you're taking, right, like people will take sort of higher amounts of ibuprofen, and what'll happen, right, though, is that you've effectively stopped the formation of this molecule, right? But what then ends up happening is you generate a buildup of this molecule, right? Le Chatelier's principle, right? If it can't go here, it's got to go somewhere. The body's got to take care of it in some way. And it turns out that there's a lot of other sort of eicosanoids that are generated, such as leukotrienes. There's this thing called TNA alpha that's like a degradation product of the sort of process before here. But that's one of the big issues with that. And then you can imagine even further, like a lot of the work with Vioxx, right? You guys might have heard of Vioxx and Celebrex. I think it was Vioxx that got pulled. I think Celebrex is still on the market, which is bizarre because I'm sure that it's the same thing, right? It effectively does the same thing. So the things that made Vioxx lead to sort of heart attacks and stuff, it's one of the great mysteries of how Celebrex is still on the market. Well, it's on the market because a lot of people, it works for a lot of people, and the risk, the reward outweighs the risk in that case. But again, a lot of these sort of manipulating different pathways have these sort of problems. When I was in graduate school, one of the things that we were sort of interested in doing, and this will just sort of put it into perspective in terms of what kind of current medicinal chemistry is doing, is the sort of question was, well, if you generate this, right, if you have this and you prevent it from going to this, but then there's all these other eicosanoid pathways, well, that's going to cause a problem. What if we can prevent the buildup of arachidonic acid? And as it turns out, there's an enzyme. Arachidonic acid really comes from phospholipids. Okay, and so you'll see molecules called phospholipids. Okay. This is a sort of choline head group up here. So you'll see molecules that are called phospholipids. And it turns out that the position, and arachidonic acid comes from phospholipids. So this is a general structure of a phospholipid. You can see it's got this sort of one polar head group over here. This is stuff that's often involved in like cell membranes and things like that. You'll see it's got these big head groups over here. And one of the sort of potential other benefits of sort of degrading this is in terms of repair of cells. So if a cell starts getting degraded through oxidative stress, on these side chains, a lot of times what will happen is the body will come in and cleave it and put a new fresh one on there and stuff like that. But anyway, you can see that there's a couple different groups that can be hydrolyzed, and they're named by different positions, but I'll just tell you that there's an enzyme called phospholipase A2. Okay, and that's going to cleave this position right here, and it's this enzyme that's responsible for arachidonic acid release. Okay, and so there's different classes of this enzyme, but when I was in grad school, we were working on this class of natural products that were sort of based on this natural product manolide. Manolide is a kind of fancy-looking compound that sort of resembled grease-like structures in a way, but had also a polar head group. It was sort of almost like a substrate mimic in a way. But what this molecule was the first of a class that were really being studied to try to prevent the formation of arachidonic acid. So the idea was, could we have as an alternative anti-inflammatory, not a molecule that disrupts it down here, but might actually cut it off at the head up here. Now again, as I sort of described earlier, anytime you cut off one pathway, there might be unintended results, but this is part of medchem. It's like you try it, you see if it's valuable, you see if the value outweighs the potential harm of it. And so again, we were working on a natural product class that actually ended up not being all that great. But around my time, it was kind of neat because I was working on this target, but I was also keeping up with the literature based around this target as well. And there was a drug that was being developed called Verisbladib. Can't remember who the pharmaceutical company. It's been now gone through multiple different groups, have now bought the rights to it. So I don't even know who owns it at this point. But this was supposed to be the first of its kind secretory phospholipase A2 drug. But I think it made it through phase 2 clinical trials for things like so sort of certain chronic inflammation, things like what do you, I'm drawing a complete brain fart right now. This inflammation in your joints. Arthritis, right? So it was used for arthritis reliefs. So that was one of the things that it was being investigated for. It was a potential drug for arthritis. And it showed some promise because that was one of the things is that they found in arthritic patients where you'd find a lot of inflammation, they would find elevated levels of secretory phospholipase A2. And so they were looking at that as potentially being a target because they thought that might have been responsible for some of the inflammation. But I don't think, so I think they developed something that was really good at inhibiting it, but I don't think it ever made it past, because I checked this morning, I think in 2012 it effectively got canned. People are still interested in studying it for various effects, but in terms of arthritis, it sort of got canned. But again, this represents an example of a target, right, that sort of makes sense within the arachidonic cascade, but I think makes sense in terms of putting in perspective how sometimes drug development takes place, right? We have a molecule that has this anti-inflammatory effect. You study it, you understand the mechanism, you understand the overall problems. There's some issues here that are thought to perhaps be resolved by cutting it off here, and so this is something that people are actively working on, and pharmaceutical companies have developed inhibitors of this, but currently they haven't shown enough efficacy to actually be used clinically, but they're continuing to try to find a value at a sort of safe base. Okay? All right, so this is arachidonic acid. Again, it's certainly a fatty acid in a way. It's a cis, it's got a lot of the cis double bonds in it. It's long, and again, now you sort of maybe understand ibuprofen a little bit more. So another class of molecules that we're going to study, there's the prostaglandins. Another class of molecules that you guys should probably be pretty familiar with that sort of involve these big greasy molecules are sort of the steroids. Right? So steroids are in general, and we'll talk about the sort of biosynthetic pathway behind them, and it'll sort of put into perspective classes of molecules that are often referred to as sort of terpenes. So previously when we were talking about fatty acids, so I should sort of make a switch here. These are not going to involve fatty acids per se. These are now, we're going to turn our attention towards terpenes. I'm going to start this talk over. Forget I mentioned steroids. Terpenes. Okay, so we just talked about fatty acids and gave an example of fatty acids. Okay, terpenes are another class of really big greaseball, important biological molecules. And they often start from this sort of, actually, this would be it right here, I think. This isoprene. That's isoprene. I don't know, I didn't write it down. But this would sort of represent a diene terpene. I think this might be isoprene, but I might be wrong. You know what, I think it's this. I think that's isoprene. But anyways, the important point here is 1, 2, 3, sorry. Since I completely misdrew it. That is isoprene. Okay? So it's a 5-carbon unit. Sorry, I was trying a 6-carbon and I couldn't remember where the double bonds were supposed to be. So this is isoprene. It's a sort of a standard, it's your sort of standard mono, it's actually not even a monoterpene. Technically monoterpenes are 10, but this is a sort of a subunit within terpene scaffold. So what you find within a lot of sort of drugs, or sorry, a lot of natural products, is this sort of 5-membered carbon sort of branched unit, right? Where you basically have a butane, it's sort of like, 2-methylbutane in a way. And what you find is that there's actually a lot of natural products and a lot of compounds that are of physiological relevance that are effectively built off of these sort of building blocks. And where they come from in general is reactions of molecules like this. Okay, and so this is a phosphate. This would be called a sort of a DPP unit. I'll make sure I get this right. Right, so this is a pyrophosphate. This is isopentenyl pyrophosphate. This is actually in your book. And what you find is that sort of in biological systems, you see a lot of molecules that are effectively based upon molecules that are based off of this sort of starting material. And so from a synthetic sort of mechanistic sort of point of view, you can sort of imagine this as being a series of molecules where effectively the alkene will effectively break down and degrade this phosphate. So you can think about this group, I'm perhaps oversimplifying a little bit, but you can sort of think about this group as being sort of a leaving group. Again, there's enzymes that will do this, so this isn't necessarily a process that's going to take place spontaneously. But this is the sort of general idea, is that you begin to sort of add up, again, here, you begin to get groups where you got 1, 2, 3, 4, 5, in this case, 6, 7, 8, 9, 10, right? So at this point, what you end up with is a molecule like this. Actually, we start from, I don't know, whatever, I'll just keep going with this to make this sort of point. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so what will happen is you get a bunch of molecules that sort of look like this, where you've got, right, in this case there would be a carbocation there, and keep adding up. But what you get is these sort of chained molecules where you get this sort of, what we often say is sort of head to tail stacking of different groups. And a major synthetic pathway to a variety of sort of terpene compounds is that you'll do a series of these transformations, right? In this case, there would still be the OP. So there would still be the OP2, O6, 2 minus. OP2, O6, 2 minus. Basically the same thing and stuff here, right? And so you get to a molecule like this, and then as you might imagine, you would eliminate, right, and sort of generate an alkene somewhere in this process. And so this overall process will keep going and going and going, and so what you'll get to is these sort of long, linear sequences that will be effectively made up of a variety of 5 different molecules. One of the ways, and I'll sort of show a few of these, and it would be good for you guys to be able to identify, I think that could be a good type of exam question, is sort of identify the isoprene units, and maybe we'll discuss some stuff like this a little bit later. But what you'll find is that there's a lot of compounds, and one of the first sort of ways that you'll often say, oh, that's a terpene natural product, is that you'll sort of count the carbons, and if it's a 5, 10, 15, 20, if it's some unit of 5, that might be an indication right away that you have a molecule that might be a terpene. And one of the advantages to that is, well, now you know how it's made biosynthetically. You might be able to engineer a bacteria if it's a really valuable molecule. You might be able to engineer something like a bacteria or a yeast to actually synthesize that for you if you want it in bulk quantities. And so it's really important sometimes for people to understand there's a whole field of chemistry that's really built upon understanding biosynthetic pathways. And so knowing whether a molecule is of this class and might be synthesized through this pathway would be important. One of the sort of key molecules, and this will transition into sort of steroids, is squalene. So squalene is a So this is squalene. Now squalene is actually kind of a dimer of 2 of them, so what you'll notice is that halfway through, it actually becomes a sort of a mirror plane. So on the left-hand side, you'll notice that the methyl group sort of is on this side, right? And on the other side, you'll notice that it sort of flip-flops. If you guys see what I'm trying to say here. If you notice the pattern here, it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? But then when you switch over to this other side, it actually skips 1, 2, 3, 4, 5, 6. But then it goes back to 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So there's this sort of symmetry to squalene. which sometimes happens. So generally, we'll often see them sort of isolated in this kind of way where it's head to tail, but squalene happens to be one where you sort of have the 5 units, right? And again, and we can go through and sort of identify, right, the terpene units in here, right? And then you sort of see over here that it kind of switches what that comes from. Okay, and so again, this is squalene. And this is actually, again, the way that what they call terpenes is kind of weird. A 10 carbon unit is called a terpene. I forget what the 5 carbon is. Maybe it's I don't remember the name of it. But it's almost like every 10. So a 10 carbon terpene is a terpene. A 20 carbon is a diterpene. This is a 30 carbon one. It would be called a triterpene. And there's other weird names in between. I don't know why they classify it that way. It was probably just that that's where many of them were in that sort of 10, 20, 30 range. But you'll find them at every 5 carbon interval as well. And they each have different names. There's like one that's called like a sesquiterpene, and there's a bunch of different names for them. But this is the important point. Okay, so for steroids, squalene and steroids are terpene natural products. And they actually come from squalene. And what's kind of neat is, as a synthetic chemist, I teach a course on occasion at the grad center, and one of the big things that organic chemists will often do, actually today's faculty candidate did his graduate work in a group that sort of uses this as a motivation in their synthesis, is to sort of predict what a biosynthetic pathway might be that might be really fancy and generate a lot of complexity, and then actually try to get that to take place in the fume hood. So they call it like biomimetic synthesis. So it's like, let's see what nature does and sort of try to leverage some of that information for how nature makes molecules to sort of do these kind of things. And some of the early work in this area actually was just done down the road at Columbia by Gilbert Stork, sort of involved sort of steroid cascade processes. So a steroid effectively, so I'm going to redraw this molecule. I totally ran out of workspace. Okay, so that's the general. It's in here that's going to be important. What often happens in sort of steroidal cascade, again, this takes place in an enzymatic pocket, yes? This is squalene redrawn. Squalene is a very simple compound that basically comes from the effective polymerization, if you will, of isopentenylpyrophosphate, so oligomerization, right? So several isopentenyl pyrophosphates, again, this would be, for example, intermediate, right? You can imagine this sort of continues to happen, right? You're going to, say, for example, generate the alkene there, another molecule will come in, do it there. At a certain point, it sort of reverses itself, but the sort of point that I'm making is that the important point is squalene is a terpene. You see all the terpene subunits in there, right? So there's 1, 2, 3, 4, 5, 6 of them. So what it comes from, squalene comes from 6 isopentenyl pyrophosphates. And the rough mechanism is to think about this group as sort of being a leaving group and this alkene being a nucleophile, as we've seen in the past. So, but the point within steroids are that squalene is the starting building block behind steroids. And I'm going to sort of show how this sort of happens. Now, within a sort of biosynthetic pathway, a lot of times nature is really efficient in doing things. And within the steroidal cascade process, nature is really good at taking the squalene, effectively sits inside a binding pocket where everything is positioned really well, and then activates this alkene, generally through something like an oxidation, for example. So as you can imagine, if you sort of oxidize this bond in some way, right, with, say, for example, say, oxygen, right? This will be totally just, obviously we're not going to sort of generate this per se, but if there's pathways that activate this through oxygen, and so this is just a sort of shorthand way to see this. There would be oxygen over here. But the point is that you're effectively activating this alkene. When that happens, you effectively generate a carbocation here. And so I'll show the sort of first intermediate for this. And once you generate that carbocation intermediate there, what's going to happen is this alkene here is now going to kick down and make a 6-membered ring, leaving a carbocation there. Okay. One, two, three, four, five, six. So that would be here. Right? And so you'd effectively do that. Does everybody see what I did here? So when you do this first transformation effectively, again, that's just sort of in quotation marks. The point is you sort of generate carbocation character. I'm just trying to show you how the connection takes place. You're effectively going to generate a carbocation here. This takes place concertedly, but I think breaking it down allows you to see it. Then what's going to happen is this alkene is going to kick over, make a 6-membered ring, okay, leaving a carbocation there. It turns out this process sets off a series of these, right, where this will go here, right? Oops, I'm missing a carbon on this here. I'll use a different color here. One, two, three, four, five, six. Right. So I have one more color. Purple. One, two, three, four, five, six. So in this case, we're actually going to generate a carbocation here. Okay. Okay, does everybody see how that happened? Effectively, this process that I showed here is going to take place effectively 3 times. So we're going to generate 3 cyclohexane rings in a concerted fashion. Okay? Pretty wild, right? What that's going to lead to, we're not quite done yet, there's one more process that takes place, because the steroids have a structure that we'll talk about in a moment. That's going to be this one. There. Here. That's going to be here. Purple would be hopefully I didn't screw this up as possible, but I did, but I don't think I did. That's going to be there, and let's see if I missed anything. So we've got a methyl group there, we've got that group there, we've got that group there, so I think we've got everything there. But you can see effectively what we've done is we've generated a 6-6-6 ring structure. Okay? If I draw this sort of flattened, what you get is something like this. Okay, so you get a molecule that looks like this. See if I'm missing any carbons. So 2 here, 1 here, there's 1 here. Okay, so that's the sort of general structure, and then again, as I sort of have outlined here, we'll have a OOH. But within a steroid structure, there's generally one more ring that's formed. Okay, and that's going to be we should still have 1 carbocation left, right? And that's going to be on this last carbon here. Right, so that's going to be right here. Okay, so that's the last carbocation. And the final ring up at the end, it's the same thing. It's all going to have it inserted, but I figured it was best to show the 6 first, redraw it, and then we can see the 5. That now the last ring is going to be a 1, 2, 3, 4. Oops, 1, 2, 3, 4, 5. Oh yeah. So 1, 2, 3, 4, 5. And what that's going to get you to is this sort of 6, 6, 5 ring structure. So if we sort of continue this, what we'll have is carbocation there. Okay, and so you'll have structures like this. So it's important within steroids. Okay, so this is the sort of cascade, right? And then you can imagine once you're at that carbocation there, some other things can happen. You don't generally generate another ring, but a lot of times what will happen is you'll get carbocation shifts, for example. So a lot of times within a steroid, you'll try to map out your terpenes, and there'll be 1 carbon that seems off, and it's because once you get to intermediates like this carbocation, like you can imagine like an alkyl shift there, for example. And so a lot of things can happen there. I just wanted to show you guys this overall process that leads to this 665 ring system, which I think is really cool and it's really impressive. And again, this all happens, this whole process. There's different enzymes that will do this for different classes of steroids, but this steroidal cascade, I think, is pretty impressive. And as a synthetic chemist, again, like I was saying earlier, one of the sort of driving forces behind a lot of the chemistry that's developed is to try to see what nature does and try to actually repeat it in a lab. And so back in the, again, 60s, several groups, namely Gilbert Stork at Columbia being one of them, did a lot of work trying to sort of harness this and develop cascade processes that would be set off in this way. A guy, E.J. Corey, worked on this stuff. One of the big sort of breakthroughs came because they kept actually getting problems over here in terms of the ring that was forming here, which is not how it's possible, but you guys get the point. They found that if you had like an alpine up there, you could actually get the 5-member ring up there. So anyways, I thought this was really cool. Again, steroids are important. They're obviously significant sort of molecules for a variety of different hormones, be it sort of testosterone or whatever. And so let me just show you guys really quickly an example of one, and we'll take a look at this, and you'll sort of see how this process plays out in it. So I think the two that you guys are probably most familiar with in terms of steroids are the sort of male and female, sort of like estrogen and testosterone, right? So those are the ones that we'll often hear about a lot. And so if we look at the structure for testosterone, again, it's important to recognize that it's not going to be exactly like this, but I'm just going to sort of use this as an example. But again, the important thing that you see in that steroid, again, is this sort of 6-6-6-5 ring systems. But you will notice some things that are different, right? You'll notice that okay, so this methyl group is where that methyl group is there, right? But there's some other cases. I think there should be a methyl group here. I haven't written down a proton, but I'm pretty sure that's a methyl. So I could be wrong there. But I think that methyl is supposed to be there. But again, here you have a proton rather than, say, the methyl group that we had down there. Again, usually that's the result of, say, for example, cation shifts that take place, like subsequent cation shifts. So you can imagine, right, this cation, this methyl group shifting over there, this methyl group shifting over, this proton shifting over there, and this methyl group shifting over there. Again, up here you don't have any of these additional carbons. Something might happen that just sort of biologically chews that unit off, so more complicated enzymes. Again, same thing with those two methyl groups there, for example. But again, you see, you look at the oxidation state there, right? It's sort of set up in the same way the oxidation state is there. So you start to see that you can't necessarily look at the steroid cascade and imagine, oh, this is how this one's made, or oh, this one's how this one's made. But you can clearly see how this sort of general scaffold looks, and at least how some of the things compare within the two. And so I thought this was neat. I thought this had a certain element of sort of wow factor. Yeah. Hmm? Yeah, that's what I was saying earlier. It's an enzymatic process. This is not, you cannot reason this based upon your principles of oh, well, if this alkyne went in and keep going, that's a great question. But what it really comes down to is that this is not a process that's necessarily run in a lab. You know, it's within a binding pocket of an enzyme. It forces it to adopt a specific conformation that allows for that and not others. And again, so that's more of an evolutionary question. You can't just take squalene, treat it to hydrogen peroxide, and expect to generate these intermediates. It's a more controlled process, but at least you can see, and again, synthetic chemists have tried to use this and leverage it to make certain modifications, like they'll build up the squalene structure with some leaving group on this other side and see if they can't get it to undergo cascades based upon cation formation. Yeah?
Well, in the metabolic process, actually you have to start with
right. Say it again?
In order to get to one of cascade.
Yeah. It all starts exactly. It all starts with the right. Exactly. It all starts with that terpene, single terpene sort of unit. Okay. So there's about 10 minutes left. Kind of things to talk about. But what I'll do is I'll show you an example of a few terpenes. Anything else we can talk about? That's pretty much it. So your book discusses certain other vitamins as well. Again, you can sort of read through that. I didn't really think it was worth talking about it. You can read about it. But I think terpenes are kind of interesting. And one of the things that's, again, I sort of stated earlier, when a synthetic chemist, again, that's primarily what I am as a synthetic organic chemist, when we start thinking about new reactions to do, we'll often sort of look to nature and ask ourselves how nature actually makes those compounds, because that might give us an idea of how to make them. So I remember when I was in graduate school, it would be very common that somebody would be giving a talk, and if the person didn't just talk about how it was actually made biosynthetically, there'd always be like a bunch of people like, what is it, how is it made? Is it known how it's made? And in the chemistry that we're doing in our lab, I think we get a lot of those same type of questions. And so the molecules that we're working with in our lab have at the core these sort of tropanoid structures, sort of shown here. And there's been a few different classes of these that have been, there's actually not too many natural products that are like this. I would say there's really 4 main ones. 2 of them which are sort of within this. Called dihydroxytropones. So these are 2 of them. You'll notice that they actually have 4 in a row. And then there's a couple others. One of them looks something like this. It's called manachol. And the other one looks like this. And terpenes, one of the main areas that people often sort of look for terpenes, these are just the natural sources, I think the four most widely studied of this class of natural products. But what's sort of interesting is that these compounds over here were really found in sort of cultures of yeasts and certain bacteria. And these two over here were actually found in trees. And one of the things that we often sort of think about in, when you start thinking about terpenes, like one of the places that you're always, people always are driven to are trees and things like pinene, right? Pinene is something that you guys might be familiar with. If you look at the structure of pinene, that could be a good exam question. Identify the units of pinene identify the terpene units within pinene. It's a very simple structure, and you can likely just pick out the two 5-numbered units within it. But again, it's really in a lot of trees that you actually see these groups. And it was recently determined that these molecules over here, on this side, sort of biosynthetic pathway was determined from these, and it ended up coming through sort of what they reasoned and what they sort of figured out that it comes through is these sort of catechol-based pathways where you'll start with a molecule. Catechol looks like this. So they're not terpenes, right? They start from this, and there's chemistry that effectively will take that, and your body or whatever the organism will take it and oxidize it and effectively turn it into these other groups. These cases, it's not known, but I think they come from trees, and certainly as interest grows in these, I think there's going to be an interest in sort of knowing what the biosynthetic pathway of these would be. And one of the things that you can sort of notice about them right away, and when people have asked me, oh, what's the source of these? I'll often say it's not really known, but this one has 7, 8, 9, 10 carbons, and this one has 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? So in these two natural products that are molecules that our lab is working on, again, it's known what the biosynthetic pathway is in these. These are generally found, this was actually found in tree bark. I forget where this one was found, but it's derivatives of plants and trees. And so they're almost certainly derivatives of terpene biosynthesis as well. So we work with molecules that are like terpene. Okay, so with that, I'm not going to just kill time here. So I'll let you guys go. Again, just as one last announcement. Actually, I want one more announcement. 2 more announcements. So the first announcement is for people that want to come to my office hours today. Again, I'm meeting with a faculty candidate at 12. I will be available after that, and I will be available before that. But I'm going to kick you guys out. Anybody that comes beforehand, I'm going to kick you out about 25 after. And if you show up, and then I'll basically, if you want to stay from 12 to say 1:30 or so. One more announcement after that is I'm hosting one last speaker this Friday, so it's going to be an organic chemistry-based seminar. It's Shengping Zheng from Hunter College. He's actually a good friend. He's up for his tenure, so this is the part where he's going, and he's giving lots and lots of talks. He's a really impressive synthetic organic chemist that does a lot of work on coming up with strategies like synthesis, like a lot of the predictions that you guys come up with synthetic strategies. That's really his go-to. He comes up with really nice and elegant ways to construct molecules. And so again, it's going to be Friday at 2:30 in 437 New Ingersoll. So it could be, I think you guys could get a lot out of it if you want to show up. And if there's anything relevant to our course that's in that talk, it may end up being on the exam.